All right, hey everyone, welcome to the Fall 2017 Midterm Review video. So in this video, we're going to be going over some midterm review questions. All these questions and the slides can be found in the description below. So if you want to go ahead and follow through, click on the link in the description. We will have these questions available along with the solutions there. In the video itself, we're going to be going over questions on the midterm. So for the Fall 2017 midterm, you guys will be covering tables and programming, histograms, probability and sampling, as well as just like causation and experimentation. So without further ado, let's go ahead and get started. So the first question we have right here is from the spring 2016 midterm, and it's about programming. The question asks, you're given an array of integers named CA, and it contains the estimated population of California every year for 10 years. So the CA array has 11 items, and the first item is the population of California in 1900, and the last is the population in 2000. So we can see that we have our array here. We can see like the first three elements along with the last three elements. And it says that it has the population of California every 10 years. So we know that this first item in the array is corresponding to the year 1900. We know that the second item in the array corresponds to the year 1910, and then the third item, 1920, and so on and so forth. So I'm going to go ahead and delete that. Okay, so with that information, we now have to answer these following questions. So we have to write Python expressions for the following descriptions that computes its value. So the first question and its answer is kind of given to us. So the population in 1900, that's just ca.item0. And you can use .item because we know that ca is a numpy array. And 0 kind of is the first index of the element because arrays are 0 indexed. So the next question, the population changed from 1940 to 1960 expressed as a number of persons, not a proportion. So in this case, we basically need to get two pieces of information, the population in 1960 and the population in 1940. With those two pieces of information, we're able to calculate the difference as a number in persons. So to be able to get that answer, it's just indexing into the array. So we know that the array is 0 indexed, so just a reminder, this first element corresponds to the population in year 1900. So we need the population of the year in 1940, which is ca.item. And because we know that the population in 1900 is .item0, we can now know that the population in 1940 is .item4. And now we also need to get the population of California in 1960, and that's just ca.item6. And to get the difference, we just subtract the two, and that's our answer as number in persons. So it's going to be ca.item6 minus ca.item4. All right, next question. The next question asks whether the population ever grew by less than 500,000 in a decade represented by CA. And in parentheses, this is true or false. So this question is a little bit more tricky because it asks for a little bit more complex answer than the first one. It wants to know whether or not the population ever grew by less than 500,000 in a decade. So the first step that we need to do is we need to kind of get the differences between each decade. So basically, in this case, we would need the differences between this element and this element, this element and this element, and so on and so forth. Luckily, we have a Python function that does that for us called mp.diff. So mp.diff, mp, if I can spell, mp.diff takes the differences of each adjacent element in a numpy array. So in this case, if we take mp.diff of ca, our resulting array is in the first element of that array is just going to be the difference between 1910 and 1900. The second element of the array is going to be the difference between 1920 and 1910, and so on and so forth. So now that we have all the differences between each decade, we're not completely done with our question yet. We want to know whether the population ever grew by less than 500,000. So to get less than 500,000, we basically need to get the minimum amounts of the population changes between all the different decades. And so to do that, we just basically take the min of this whole difference array. But we're not quite done yet because it asks for like a true or false statement. So now we basically have a minimum amount. So this is just like one integer right here. This is just one integer, and we just basically need to compare it to the number 500,000 to see if it's less than that or not. So we basically just write less than 500,000. And with that, we have our answer to question 2. Moving on. Okay, so this part now we're asking for the annual yearly growth rate from 1920 to 1930. So we know that because it's asking for the growth rate, we have like our growth rate equations from just like the worksheet or from class itself. So just kind of remind you guys what the growth rate equations are. Because we're asking for the annual growth rate from 1920 and 1930, we know our kind of initial and after values. So the actual growth rate equation is going to be after divided by before, all raised to the 1 over t, where t is the amount of time that you have minus 1. Okay, so in this case, to answer our first question, we know that we know what the annual kind of like before and after values are. So the before value is basically like the population in 1920, and the after value is the population in 1930. So we basically first need to get those values. So we know that the after value is going to be the population 1930. So that's just CA dot item 3. And we know our before value right here is going to be the population 1920. So we do CA dot item 3 divided by CA dot item 2. We have to write this in the Python expression. So let me just erase that. So to write this in the Python expression, it's just CA dot item 3 divided by CA dot item 2. Okay, so now that we have those parts of our equation, we want to raise this value to 1 over t minus 1. And because we know that the difference between 1930 and 1920 is 10 years, that makes our lives a lot easier. So we just raise this to 1 divided by 10. And then we complete the rest of our equation, minus 1. And so now we have the answer to the equation for the annual growth rate from 1920 to 1930. So this is all equal to growth rate. Okay. Next, the question asks for the population in 1924, assuming a fixed exponential growth rate from 1920 to 1930. And it says you may use the name G for the annual growth rate from 1920 and 1930. So we're given G, which is our annual growth rate. And because we can now assume that there's like a fixed exponential amount of growth rate from 1920 and 1930, we can actually get the actual like population estimate for 1924. Notice how we don't have like the year 1924 in our array. We only have the year 1920 and 1930, but we can kind of extrapolate the fact that we have the growth rate to calculate the population rate in 1924. So to be able to do this, we first need to start off with like our base growth rate year. And the equation that we want to use in this case is just x times 1 plus the growth rate raised to the time. Where x is kind of your initial value, g is your growth rate, and t is the amount of time that passes. So we start, because we know that we only have the values from 1920 and 1930, we want to start with the population in 1920. So to be able to get that item, we do CA dot item 2. And we multiply CA dot item 2 with the rest of our equation. Oh, that's a mistake. Okay, so we multiply CA dot item 2 with the rest of our equation, which in this case is just 1 plus G. Remember that we're given G. G is the annual growth rate from 1920 to 1930. And because we know that 1924 is only 4 years after 1920, in this case, our T is just going to be 4. But we're doing this as a Python expression, so it's going to look something like star star 4. Star star 4. All right, now the last question. It asks for the number of items in CA that are at least twice as large as the population in 1960. So to be able to do this, we have to first get our population in 1960. So let's just start with that. CA dot item 6 corresponds to our population in 1960. Now it's asking for the number of items in CA that are at least twice as large as the population in 1960. So we're going to have to be able to use some like array, just like comparison array arithmetic to be able to get our actual answer. So it's asking for at least twice as large. So we're going to have to compare all the values in CA to the 1960 population, but it's twice as much as the 1960 population. So in this case, we have to compare CA to 2 times the population 1960. Now we're going to need to have the number of items that are greater than that. So to be able to do that, we actually have this function called mp.countNonZero. And if you guys don't remember what mp.countNonZero does, go ahead and look in the textbook or look on your worksheets to figure out what it does, because it's going to be really useful for the midterm. So what it basically does is it counts the number of true-false values in an array. So if we were to compare every value of CA to 2 times CA.item 6, with just like a greater than or a less than or equal to like Boolean expression, it would give us an array of true-false values. So because we're counting the number of CA items that are at least twice as large, we want to see the number of items that are greater than or equal to 2 times CA.item 6. And to be able to count the number of values, we just do mp.count non-zero of this entire array. So what this expression returns is an array of true-false values. So it's going to compare every item in CA to this number. So it compares this first value right here to 2 times the population 1960, this value right here to 2 times the value in 1960, and it just returns an array of true-false Booleans of whether or not that population is greater than 2 times the population 1960. And then you can use count non-zero to count the number of true-false values, so you get the minimum number, the number of items that are at least twice as large as the population 1960. Okay, cool. Now we have a probability/programming question, also from the spring 2016 course. So this question itself, it asks, you're given 1,000 different shirts in a huge closet, but only 2 of them are red, and each morning you pick one uniformly at random, wear it, and then put it back at night. So let's go ahead and underline put it back at night. The question asks to write a Python expression to compute that the chance that during a 30-day month you never wear a red shirt. So going back to kind of like basic probability rules, we know right here, because it asks that we put it back at night, the question is asking with replacement. So the chance that you kind of wear a red shirt on just one given day, because you only have 2 red shirts out of 1,000 different shirts, it's going to be 2 out of 1,000. So that's the chance that you wear a red shirt on day 1. The chance that I wear a red shirt on day 2 is just going to be 2 divided by 1,000 times 2 divided by 1,000, or 2 divided by 1,000 raised to the second. Now the question isn't really asking like, oh, what's the chance that you wear a red shirt every single day of the month, but it's asking what's the chance that we would never wear a red shirt over a 30-day month. So in this case, we basically want to take the inverse of what we calculated before. So the chance that you wear a red shirt on a day is 2 divided by 1,000, but the chance that you'd never wear a red shirt on that day is 1 minus this value. In this case, if we're doing the chance that we never wear a red shirt over 30 days, it's going to be 1 minus 2 divided by 1,000 raised to the 30. Because we have 30 days, and we're looking at the number of days that we never wear a red shirt, which is going to be 1 minus that value. All right, so I just realized that this question asks for Python expressions, and I ended the last part just with an expression. I think it was like 1 minus 2 divided by 1,000 to the 30. So to convert that to a Python expression, it'd be something just like 1 minus 2 divided by 1,000, star 30. Yeah, so that's going to be your final answer for this question. Yeah. All right, so the next question we're looking at is from spring 2016. It's a tables question. So we're given a table called trip where each row from lecture describes a single bicycle rental in the San Francisco area. So we can see we have a nice kind of snippet of our table right here. We're given our start and end destinations, which are represented in strings, along with a duration column, which is just like the duration of the trip. So the question asks to write Python expressions below for each of the following descriptions, and that computes its value. So the returning like line that you write should return like that value that it's asking for. You may use up to 2 lines and introduce variables. So that is super important. We're going to underline that. So the first question asks for the average duration of a rental that lasted more than 2 minutes. So in this case, the first thing that we should do is we should filter our table for the rentals that only lasted for more than 2 minutes. So to be able to do that, we have to do something like trip. And remember, to filter tables, we use the where method. So trip.where. And we're filtering on trips that only lasted more than 2 minutes. So we're filtering on the duration column, so duration. And we're looking at trips that lasted more than 2 minutes, so we got to do r.above. And our duration column right here is in seconds, so we just have to convert 2 minutes to 2 minutes to seconds, which is just 120 seconds. So this is our filtered table of only trips that lasted more than 2 seconds. Let's go ahead and assign that table to a new table called 2mins. So then again, this is a table that looks exactly the same as our original trips table, but it only includes the trips that lasted more than 2 minutes or 120 seconds. And now it's asking us to find the average duration. So what we can basically, the average duration, so what we can basically do now is we can select that column, the duration column. So we take our 2mins table, and then we select that column. So we do .column, and we want the duration column. And to be able to get the average, we basically take the sum and divide by the total number of elements. So we take, let's use mp.sum to take the sum of each element in durations and divide that by the total number of things in 2mins, which in this case is just 2mins.num rows. So we use 2 lines, and we now have the average duration of the rental that lasted more than 2 minutes. Second part of the question is asking for the number of rentals that started at the SF Caltrain station. So we're going back again to using our trip table right here, and we just basically want the number of rentals that started at the SF Caltrain station. So because it's asking specifically for the SF Caltrain station, we can just filter on that value. So we just do trip.where the start location, so start, is equal to SF Caltrain. So when we're looking for equality, we don't have to use we can use r.equal to, but we can also just pass in the value as the second argument. So we can just pass in SF Caltrain. So now we have a table of only the trips that started at SF Caltrain, and if we wanted the number of trips, we can just take .num rows. Okay, moving on. So now we have 2 more parts of the same question. The next question asks for the name of the station where the most rentals ended, assuming that there are no ties. So to approach this question, we need to know that there are kind of multiple trips that start at different locations but end at the same location. So to be able to look at a question like this, we have to kind of figure out what are all the unique values for the trips that ended for the SF Caltrain destination or the second at South Park destination. And to do this, we basically have to group on our end destination table. So let's go ahead and start with that. We want to do trip because we're using the same trip table. We want to look at all the number of trips that ended at a certain destination. So we want to group on the end column. And because in this case, we're just looking at the number of things, we don't need to pass in another aggregate function to group because we just need the counts. So if we just do .group of end, it gives us the counts of all the trips for that table. So what this will do is it's going to create kind of a 2-column table where your first column is going to be like your end destination and your second column is just going to be count, where that's like the number of times that, like number of trips that ended in that destination. So now we have like our table and we just needed to find the name where the most rentals ended. So to be able to do this, there are multiple ways, but the way that the method that I like using is just sorting. So I can just sort, and I can just sort on the count column right here. So I can sort on count. And then I want to make sure that I get the most rentals. So I want to make descending equal to true. And then because I know, because it's all sorted now we're just asking for the name of the station. So I can just take the name of the station, so column 0, and then so that returns me an array of all the destinations, and I just want the first destination, so I can just do .item 0 in that case. And that gives us our answer to the name of the station where the most rentals ended. Okay, and now the last question for this part is asking for the number of stations for which the average duration ending at the station was at least 300 seconds. So we have a lot of stuff going on in this last question. Because it's asking for the number of stations, again, we know that we want to group by something. But in this case, we're not grouping by like our end column. We're grouping by for which the average duration ending at that station was at least 300 seconds. So we need to first figure out that because we only care about the average duration ending at that station, we actually don't need this start column. So the first thing I'm going to do here is I'm going to select a table just with these 2 columns. So I can do select 1, 2. And this just returns to me a table without the start column. So we don't really care about the start column, so let's get rid of it. So it returns to me a table that looks like this. And now we want to basically first group by the end stations. So it's asking for the number of stations for which the average duration ending at that station. So we want to group at that end station. So we do call .group again, and we use end. But now it's asking for the average duration. So because it's asking for the average duration, we don't want the count again, but we can pass in another aggregate function into our group method that gives us the average. So we can just type in mp.average. And that gives us a 2-column table, kind of like this table up here, but instead of count, it's going to be called duration average. So duration average. And now that we have the average of each the average duration of each ending location, we can take that duration column and compare it to the number 300. So we need to find the number of stations that the average duration was at least 300 seconds. So we first need to basically select that column, so the duration column. So to be able to select that column, do column 1. So this returns our duration average column, where each average duration corresponds to the ending destination. And we can basically compare each individual value in that kind of duration average array to the number 300. And because we're writing in Python, we need to do greater than equal to 300. So now we just have an array of true false values where each number in that array corresponds to the average duration and whether or not that average duration of that ending destination was greater than or equal to 300. It's a lot to say. Okay, so now we have our array of true false values, and we just have to get the number of stations. So we have that nice function called mp.count non-zero, which counts the number of true statements in your array. So we just take mp.count non-zero of this entire statement right here, and that gives us our answer to part 4. All right, so now I'm going to hand it over to Howard, one of our tutors, who's going to go over histogram problems.
Hey guys, how's it going? I'm Howard, and we're going to go over the histogram questions from spring 2016, which is, fun fact, when I took the class, so great. Okay, so the first question is, these give us distributions from the table before. And if we look at the table before, you'll notice that there's a start and an end and a duration. So this gives us a distribution of the durations from that table. So these are both histograms that represent the durations of the same table. So this represents the same data, except just gives us different bin widths, which is perfect for testing conveniently. So the first question is, write the proportion of trips that fall in each range of durations below. Show your work. If it is not possible to tell from the histograms, instead write not enough information. Great. So the first one is the proportion of trips that fall between 200 inclusive and 400 exclusive in seconds. So the first thing we're going to look at is we're going to look at the bins of the histogram. So from the first histogram, you'll notice it goes from 0 to 200, and then 200 to 400, and then 400 to 600. So conveniently, that's going to be perfect for what we're doing. So we know that the area of the bin widths in any histogram represent the proportion of data values in that bin, right? So we're looking from 200 to 400. So what we're going to want to do is look for the proportion in the bin, for the area of the bin width, right? So the first thing we're going to do is look at the width of the bin, and that's 200 to 400, and you'll look over here, 200 to 400. So that's 200, right? So it's 200. And the second thing we need to do is we need to find the height, right? And if we go from here, you'll notice here is 0.15 or so percent. But this is percent per second, right? So we're going to have to take 0.15% and then convert that into a percent. So that's going to end up looking something like this. It's going to be 0.0015. It's 0.15 of a percent, and then that's going to give us our whole answer. This ends up coming out to something around 30%. But that's not going to be important for the sake of the test because we're only going to be testing you on the fact that you know how to read this histogram. So for the next question, it asks the same exact question except between 300 and 900. Again, we're going to look for the area of the bins inside the histograms. So we're going to look at the second histogram. So if you look at the second histogram here, you'll notice that it goes from 0 to 300, 300 to 600, 600, 900. And this is a little difficult to read because they don't give you the exact numbers, only 200, 400, 600. But we know because it stops in between the line that it's 0 to 300. And conveniently, 300, 900 also falls perfectly within that bin width. So what we're going to want to write is we're going to want to do the area once again, similar to before, except of these two bins from 300 to 900. So the first one will be 300 to 600. So what we're going to do is we know the width of this bin is 300, so we're going to put 300 here. And then we're going to want to multiply it by the height. And the height, we'll notice here, is around 0.14. So here it's going to be something like multiplied by 0.0014 for the similar logic of previously. And then we're going to want to add on the height of the second bin, right? So the second bin is also 300, so it's going to be plus 300. And then we want to multiply it by the height once again. So it's something like 0.08. So we're going to multiply that by 0.0008. Similarly to what we have previously in terms of the height of the bin width. In terms of the height, we know that it's percent per. So because it's something like that, that's what we're going to want to give. Again, writing this query out is enough as it demonstrates you have an understanding, deeply understanding of how histograms work in terms of their height and their areas. Now, moving on, part C. So in the test, these will be all part of one question, but we put them on separate slides, for convenience sake. So this one says, write the proportion of trips that fall into each range of durations below. Show your work. If it's not possible to tell from the histograms, write not enough information. So this one is going to ask from 400 to 900. Now, this is going to be an interesting question, right? Because from here we have 400 to 600, and 600, 800, 800 to 1,000. From here we have 300 to 600, 600 to 900, 900 to 1,200. So immediately we know from a fact that we cannot tell the distributions of data points within a bin because all of them could be on one side, all of them could be another. Because of the size of the bin, we don't know where we can find the data point. However, we do know that both of these histograms represent the same distribution of values. So that means that we can use information from both of them in order to determine the values that we're going to want to get. So that being said, the first one we know is we know that this one can give us the exact value of the proportion from 400 to 600 right here, 400 to 600, right? And we know on the second one, we can get one from 600 to 900, conveniently the size that they asked for, 400 to 900. So the first thing we're going to do is calculate 400 to 600 like we did in the previous problem. So it's obviously just going to be the width, is going to be the area of the bin. So it's going to be something like 200, which is the area. And we're going to multiply that by the height of the bin, which is 0.14% of a percent. So it's going to be 0.0014. Ooh, that is not what I want to do. Okay. I'm just going to write 4 here really quick. There we go. 200 times 0.0014. And that's from 400 to 600. And next, we're going to find 600 and 900 from the second histogram. So we're going to add that to 300. And then 300 is the width from 600 to 900, obviously. And we're going to multiply that by the height multiplied by 0.0008. So that should make sense, everyone. We can use the information from both histograms in order to tell a convergent set of values. Yes, and I'm going to erase this really quick, see if this works. There we go. Okay, great. So on to the next problem. This is from 200 to 300. And again, this falls in line with some of the other problems that we've seen in terms of using both histograms. These are questions that are very easy to trick students with, right? Because we see 200, 300, we notice that none of the bins fall in line perfectly with that, and then we decide, okay, it's not information. There's no way we can do it. But if we look at this, we're going to see that there is quite an interesting way to do it. So from here, on this data point, we have it from 200 to 400, right? And then 400 to 600, right? So for here, we have 200 to 600. Over here, we have it from 300 right here to 600 right here, right? So we know from 300 to 600, we know that data value, right? So given that information, that allows us to deduce what 200, 300 was, right? Because what 200 to 300 would be what 300 to 600 is, what 200 to 600 is minus what 300 to 600 is, which would give us 200 to 300. I know that's a little confusing, but just bear with me. I would recommend you, sit down and think about this really hard. The harder you think about it, the better it goes. So what we're going to do is we're going to find that information with 200 to 600, which we have done previously, right? So it's going to be the width here, which is 200, and we're going to multiply that by the height here, which is 0.0015, right? And then we're going to add that to this 400 to 600 plus 200. And we're going to multiply that again by the height, which is 0.00 about 14. And then we're going to take 200 to 600 and we're going to subtract that. We're going to subtract 300 to 600 of that to find 200 to 300, right? So we're going to take that and we're going to subtract 300 to 600, which we know is from here to here, from here to here. And then we're going to do 300 is the width, and we're going to multiply that by the height, which is around 0.0014. 0014. So that's going to give us the answer to the last problem. Yeah, so this should, to make it simpler for you, I'll just write some parentheses here. This is the total, the total values you're going to want to be differentiating by. Again, 200 to 600, 300 to 600. If we subtract the 2, then we're going to end up getting 200 to 300. Okay, so that's that. Now, the next couple of questions I'm going to be doing with all of you is some qualitative questions. They're going to be, about observations, about controlled experiments, and we'll go through them and just discuss. It's really important to know these qualitative questions because this class is not just about coding. It's about, understanding how data is conducted, how experiments are conducted, how we draw conclusions in the real world. So this is causation association, also from Spring 2016. This is practically a midterm walkthrough. But a study followed 369 people with cardiovascular disease randomly selected from hospital patients. So we'll see here that says randomly selected. Cool. A year later, those who owned a dog, so it seems like owned a dog might be important, were 4 times more likely to be alive than those who didn't. So, okay, so sounds about right. I like dogs. Dogs are great. Maybe they cause you to be alive. So the first one, circle true or false. The study is a randomized controlled experiment. So for reference, let's remember what a randomized controlled experiment is. A randomized controlled experiment is when every possible confounding variable is randomized in the experiment. So that allows us to determine something very important in data science, ending up being causality. So is this study is a randomized controlled experiment? It is not. So we're going to circle false here. And the reason it is not a randomized controlled experiment is because the study doesn't randomize every aspect of these observations' lives, right? We don't control who owns a dog, who doesn't own a dog, and make sure all aspects of their lives are the same in order to determine causality. So ultimately, we're gonna find out that this study is not a randomized controlled experiment because we don't know who owns a dog or who doesn't. All we did was we randomly selected those hospital patients and then looked at their status of whether or not they had a dog. So this randomly selected here is not enough to make it a randomly controlled experiment. So, second, the study shows that the dog owners live longer than cat owners on average. Now, this one should be more given than the first one, and obviously it's not true. And the reason it's not true is there's no mention of cats anywhere in this whole question. So, I'm just going to put no mention of cats. So that should be enough for you to be like, there's no comparison, there's nothing to judge it off of. No. So I'm going to write a quick description for the first one as well. Didn't control dogs. Just so you have a reference as to the basic logic of what we did. Second of all, and the last one is going to be circle true or false. The study shows that for someone with cardiovascular disease, adopting a dog will probably cause them to live longer. And again, the answer here is false. And the reason for that is because it's not a randomized controlled experiment, because it's just an observational study, we might be able to determine some kind of association, given an association is any relationship. So, given that dog owners live longer, they might live longer, that might be an association. However, it is not enough for us to determine that as causality. Because it's not a randomized controlled experiment, there might be the presence of confounding variables. So, what I'm going to put here is not RCT. So we know it's not a randomized controlled trial or randomized controlled experiment or whatever you want to call it. And so this leads to confounding variables. So the presence of confounding variables would detract from the possibility of there being causality. Probably don't write that on the test, but that's going to be a basic of the reasoning. So.
All right, so the next question is a visualization question from fall 2016. I think this is the first question, not from the spring 2016 in this video, but let's go ahead and look at the question. So the graphic below appeared in the front page of the Daily Cal on Tuesday last week, Tuesday in fall 2016. And we can see that it's a visualization of campus crimes from 2013 to 2015. So the question asks, one important choice made by the graphic designers makes it difficult to visually compare the numbers of crimes in various categories. What was that choice and why does it make it difficult to compare the visual comparisons? So if we take a closer look at the actual visualization right here, we can see that we have these robberies and it gives us the number of counts, the number of robberies that occurred in 2013, 2014, and 2015. But then we can also see, we see liquor law arrests, hate crimes, and sex crimes. But if you look closely at the numbers for robberies range from 9 to 23, while the numbers for liquor law arrests range from 24 to 36. And then hate crimes range from 2 to 9, and sex crimes range from 13 to 15 for those following years. So what stands out right here is the fact that these scales, these scales right here, they don't correspond with the scales of the other questions themselves. So in that case, So we can see here that the reason that they made a different kind of like choice in terms of like the numbers, but the scales all look the same. So we're comparing numbers of 9 to numbers of 24, and we can see the heights of that. The height for this bar under robberies of 9 is actually higher than the bar under liquor law arrest for 24, and that just makes it very misleading. So in this case, why does it make it difficult for the visual comparisons? The choice not to include a uniform height scale between different categories. So no uniform height scale between categories. So because of this, it makes it very difficult to compare each category, like robberies, with liquor law arrests or hate crimes. All right, so moving on. Now we have a question about studies from fall 2016 as well. So in a public health study of the effect of smoking, participants were separated into groups according to gender and age. In each subgroup, the observation was the same. Those who had never smoked were on average somewhat more healthy than current smokers, but the current smokers were on average quite a bit more healthy than those who had recently stopped. So based on these results, should the current smokers have been advised not to give up smoking? And if not, provide at least one factor that helps explain this observation. So just looking at the information that's given, we can kind of assume that no current smokers should have been quit to advise. So no, let's get rid of that. No current smokers should have been advised to quit. And the reason behind this explanation, there could be a bunch of explanations, but one plausible explanation is that those who had recently stopped smoking might be in extremely terrible health, which actually motivated them to stop smoking. And they're kind of getting better, but their current state is kind of worse than current smokers. So let me just kind of summarize that real quickly. Those who stopped smoking might be in extreme terrible health, which motivated them to stop smoking. I apologize for my handwriting. I know it's really difficult to read, but that is like a kind of plausible explanation of why, based on these results, they should be advised to quit. And now I'm going to go hand it off to Howard to go over iteration.
Hey y'all, I'm back. A nice little jolt of a different person and a different voice to keep you awake. Maybe you're asleep and did not even know I'm a different person, but you know, it's okay. That's life. So we are gonna go over iteration, which is a really powerful tool in terms of allowing us to do the same thing multiple times, which becomes a really powerful tool in computing and in statistics because it allows us to resample or redo things in multiple times and do them over. So we're going to go over a question about iteration and sampling. So stick along. This is quite a ride. Especially when I first did it. So you are given a dice and you are allowed to roll the dice 500 times. If the dice returns the number 6 over 12% of the time, then you are a winner. Unfortunately, you are given a 9-sided unfair die with the values 1, 1, 2, 3, 4, 5, 5, 5, and 6. That's a lot of numbers. Will you still be able to win the lottery? Write a function that rolls this die 500 times and computes the proportion of 6s in your rolls. If it's higher than 12%, return true. So I'm going to walk through this question and try to walk you through what my mindset would be if I were first approaching this question. So the first thing that we know we have to do is that we have this def roll die. Die is equal to 1, 1, 2, 3, 4, 5, 5, 5, 5, 6. And the first thing we want to do is, okay, we know that we're going to want to do it many times, right? We know we're going to want to do it 500 times specifically, because we're going to roll it 500 times. So we're going to write a loop here that allows us to do something over 500 times. And you know the structure for a loop. If not, I recommend going back into your textbook or into the lectures. But the structure goes like this. It goes for, and then a dummy variable. We're going to use I in. And then we know from 1 to 500 counting by ones, it looks something like this. NP dot a range 500. Ooh, okay. So we know that we're going to do that 500 times, right? And now we know, okay, if whatever we put inside this for loop is going to happen 500 times. The second thing is, okay, what do we want to do? So what we know we want to do is we want to sample from this 9-sided unfair die to see if 12% of our rolls will become the number 6 or more. Or more than 12% of our rolls are the number 6. So that allows us to be like, okay, we're going to want to do something like select values out of this array. However, we're going to have to start with an array to put it into an empty array, right? So that's sort of the jump that you have to make. We have to realize that, okay, we can resample multiple times, but resampling doesn't mean anything if we don't hold on to the value that we extract when we sample, right? So what we're going to do is we're going to initialize a new array that's empty, and then we can add values onto that array as we move. So the first thing we're going to do is something like this. We're going to do results above the for loop. We're going to initialize the array with an empty array. We're going to make array. Now, this gives us an empty array, and it's named results, right? So now that we have an empty array, we can start tacking on values to results per every 500 times, per every I in the 500 that we do it, right? So it's going to be something like this. Every time we do it, we're going to want to set results to be equal to np.append results. So now, we know np.append adds on a value to the results array every time we do it, right? So, and we know we want to select a random choice from this unfair die. And our die is 1, 2, 3, 4, 4, 5, 6, 5, 5, 6, whatever, right? And one thing we can do to select randomly from this die is np.random.choice. So we're going to do np.random.choice. And then we have the array die initialized here in our function. So we're going to do something like die. We're going to do something like that. Okay. So now we know that inside the for loop, we have a range 500 times. So it happens 500 times. We have results. And then every time we're going to append a random choice from die onto the results array. So after the loop, results should be an array of length 500. Every element in the array being a random choice from this unfair die. So now we have that. We know that we have results, and it's going to look something like, results will look something like this. It will be like an array, and it will be like, 1, 1, 5, 9, etc. ... And it should be 500 long, right? All the different ones. Now, what we're going to want to do is we're going to extract the number of those values who are 6s, because those are the ones that matter to us, right? So what we can do is we can initialize like a new variable that tracks the number of 6s that are in there. All right. And one of the beautiful things that we can do is we can do, as Wilton was speaking about earlier, np.count non-zero. So I'm just going to write this down really quick. So it's going to be number of 6s, right? And how are we going to find the number of 6s, right? So we're going to do np.count non-zero, 0. And we want to do the number of 6s inside our array that's results, right? So we're going to do results equals 6. Now, remember what Wilton was speaking about earlier. When we do results equals 6, that returns an array of true, 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 false, 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 true for all the ones that it's equal to 6. So if it's not equal to 6 in this array, like for here, it would be false. For here, it would also be false. And then once it gets to 6, it'll be a true value. And then when np.count non-zero counts the number of trues that are in there, and then gives us the number of trues, right? Now, what we want to do is remember that our function, we want to do write a function that rolls this die 500 times and computes the proportion of 6s in your rolls, right? And if it's higher than 12%, return true. So what we're going to want to do is we're going to want to initialize a new, what we can do is we have the number of 6s in a variable, right? And we know there's 500 total of length because we do this 500 times, we're rolling it 500 times. So we're going to do proportion equals the number of 6s in this results, in result, the number of 6s in result, which is num6s. And we're going to divide it by 500. And that gives us the proportion. And then what we're going to return ultimately is we're going to return a Boolean. Because if it's higher than 12%, we want to return trues. Otherwise, we want to return false, right? So we're going to return a Boolean that says this is greater than 12, a proportion of 12. So because if it's greater than 12, we want to return true, right? So we're going to do prop is greater than 0.12, which is 12% of the proportion. So once we're able to find whether or not it's 12%, we ultimately return the Boolean value. So if prop is lower than 12%, the function after calling it will return something like false, and otherwise it'll return true. So that's a walkthrough of this question. This question is a lot, and there's a lot of things going on in the question. But when you break it down in the end, you need something like a for loop to simulate doing something multiple times. You're gonna need to initialize an array that allows as a new array that allows you to pin values onto it. So ultimately, this is the thought process behind it. So that's gonna be it for the entirety of the video. Best of luck on your midterm. Wilton and I are both on the course staff, and his name is Wilton. My name is Howard. Our email is on the course staff, so email us if you have any concerns. So good luck.